What I'm going to do is I'm not going to get into a lot of the theory. I'm sure you I don't want to replicate what Mung has in his lecture, but I want to kind of frame the problem, and then I'll kind of summarize at the end on some optimization areas around this interesting question. And this is one that I think, as Mung said, does touch all of us in our daily lives. It's not an abstraction as much as a reality. And also touch on some of the history and some of the real practical areas where this is something that touches over daily lives. So I want to kind of just tell a little bit of the structure of my talk today. I'm going to first give you an overview about what is our Wi-Fi configuration at home and kind of generally in a public Wi-Fi network. When I speak to public Wi-Fi, I'm referring to the Wi-Fi that you have in hotspots at airports or at your coffee shop and so on. And what are the problems that you experience there, and what are people doing about it? So I think there is certainly some very straightforward configuration type areas, and then there are some more complex things that touch into network design, the things that are interference that we just covered and talked about, and there are things in security as well, which are actually equally important as we look into things in privacy and authentication and impact to the way we use the medium. And then I want to talk about where is Wi-Fi headed. So there's a lot of changes coming about as it becomes more ubiquitous, and a need for it for subscribers and users to actually do Wi-Fi handovers and actually use it not just in a stationary environment but actually in a more a mobile environment. And I'll kind of summarize and actually point to some opportunities and optimization problems that you expect in the future. So first, to kind of give you a perspective, when you kind of look at Wi-Fi, and this is San Francisco, and you look at Wi-Fi detect, and this is from a kind of a drive test. This is, again, public domain information done by a company in the Bay Area. You'll find that the Wi-Fi detected in the San Francisco metro area is pretty ubiquitous. Other than some parts of Golden Gate Park and a few areas around the Presidio area, you'll see that Wi-Fi availability or detected, and this is a Wi-Fi signal strength, so this is actually the strength seen by a survey tool, is very good, or at least detected across the board. When you actually start looking at to see where is public Wi-Fi, and both from a commercial network perspective and free network perspective that's available for the general public, it drops into very few areas, and you can kind of see that. The rest of it is basically personal Wi-Fi hotspots that people have in their homes. Okay, I will touch on a couple of things in the industry. One a few years ago, probably about 7 or 8 years ago, that a lot of companies were looking into what's called Muni Wi-Fi, which is municipal Wi-Fi availability across the municipal area, and companies like Google looked into building a Wi-Fi network accessible to everybody across an entire town. And for engineering economic reasons, some of those were abandoned. There is something else called FON, which is a kind of a social aspect to Wi-Fi, which allows people to share their personal Wi-Fi with others in their social network. And that is something that's more popular in Europe than in the States, but is another aspect of Wi-Fi availability. And both of those, the Muni Wi-Fi and the social network aspect of Wi-Fi, actually pose interesting network design problems that become optimization as to what the number of subscribers you want to be part of that network to get ubiquitous coverage at the same time, do it with the most economic solution. Part of the density you're seeing of public Wi-Fi, and I don't have a heat map here that shows the number of Wi-Fis detected, but you can see from the steep hockey stick curve there, the number of Wi-Fi networks increasing in the world. Just over the last 3 years, you can kind of see what's happened to that curve. So it is certainly a very fast-growing availability into the network. And feel free to ask me any questions as we kind of go through this presentation. So when we start looking at Wi-Fi speeds, from an air interface perspective, there's certain parts of the speed detected by your adapter. But another aspect of speed is really what we kind of call the backhaul speed. And the backhaul speed is a shared medium that goes from the wireless access point back into the core network. And generally, these can be limiting factors depending on the area. And in the past, these could be as low as T1 rates, T1 being symmetrical 1.5 megabits. So while you may connect at 10 megabits per second, you may actually have a throttle point in terms of the backhaul. And a lot of these have increased, but generally, just to give you a sense, shared backhaul is definitely a limiting factor in public Wi-Fi. And another aspect is the admission control of subscribers coming into it may have a diverse set of applications that actually are used, and based on how bandwidth hungry they are or greedy, you actually have starvation for other users. And I think you saw some of that in the demo that was done previously, where you had 3 users and one of them kind of grabbed the bandwidth and starved the other 2. So the fairness element does not quite exist there, and that's one of the issues. This is a paper actually done by done with AT&T by one of one of your researchers who was here a couple of years ago with an Infocom paper. And this characterizes a busy hour pattern at Starbucks Wi-Fi, and it tells you in terms of number of arrivals occurring by weekday and weekend. So you can actually see in 15-minute bins what the subscriber arrival rate is. And at those peak intervals where the subscribers are coming in, if you kind of even average it out at about 6 to 10 subscribers, and you can think about the shared bandwidth they may have at a Starbucks and say that's divided across these, assuming fairness. But if one of the subscribers has a very greedy application, you may have starvation for the other. So that's part of the challenge. And that's what's kind of listed in the next slide here. And using not throughput, but time to first byte, or the latency, the delay associated with the application. And when you look at the delay factor here over time, you can see that the average latency for subscribers, just a single user there, is about 148 milliseconds. That is the round trip time associated for a round trip from request to arrival of the first byte back from the destination site. And then when you kind of look at with a single BitTorrent subscriber in there running a greedy application, what happens is the latency increases from 148 milliseconds on average to 772, and then you have a lot of jitter. Jitter being the delay variation between the arrival of the different packets. So you actually have a lot of jitter, and jitter is actually the enemy of applications like voice and video. So anything that requires more consistency and a play-out buffer that requires consistency is the enemy. So basically, you can have something like a BitTorrent, a P2P application occurring there, and by the way, that's just illustrative. There are a lot of other applications that are equally greedy, but you can have kind of the analogy here as to the lack of fairness in that. So one of the key aspects is the lack of quality of service and kind of driving a poor experience in what you experience in a public Wi-Fi. This can actually occur on a home Wi-Fi as well. However, the admission control is something that is controlled by the population of the home. So it's something more deterministic as opposed to non-deterministic in a public Wi-Fi spot. When we start looking at the home internet speeds, and you try to determine how this compares to the public Wi-Fi bandwidth available, I wanted to kind of point to an FCC study, and this was kind of an interesting study. I think this is fairly recent. I think this is 2012, and it's also informative relative to kind of public perception, that the bandwidth that your service provider provides you at home relative to what's advertised, how does that stack up? And as you can see, across all the service providers in the U.S., it's a 96% on average as to what the actual bandwidth you're getting to what's advertised. So it is very, very high. If we look at the pie chart there on the actual internet speeds at home, less than 5% is, or about 5% is the 1 megabit rate. And you can see most homes are now served in a kind of a 3 meg to 10 meg rate, or 10 meg, 3 to 10 meg is about 16%, 10 to 20 is about 20%, and then your 10 to 20 to 30 is in the 38% range. So you have a increased number of subscribers having pretty high internet speed rates, and then also getting the advertised prices. As things have moved to Ethernet and IP-based, with reduced overhead from the legacy ATM networks. So basically, your home network now gets you more bandwidth, and as a result, even if you kind of assumed a 3 to 6 megabit data rate in kind of the lower tiers, you still have a much more deterministic experience that you can manage with the applications at home, as opposed to a shared bandwidth environment. So shifting from kind of the transport network and kind of the application one to one of the big challenges in kind of the public space is authentication and security administration. And the trust aspect and the number of networks that you see is one of the key problems. And there's various security problems, but I'll kind of start with the first one on trusting the actual network. And there are several risks that I think drive some of the security procedures and mechanics, both on the client side and the service provider side, that actually constrain your experience in that public Wi-Fi use. So I won't cover, in interest of time, kind of all the various type of security problems that can plague you as you try to determine a trust associated. But some of these actually, in particularly the things on the free public Wi-Fi and some of the bugs associated at an operating system level, can actually cause at a client level for you to try to connect to a non-existent network and without realizing both expose the client, and in some instances actually add delay as you're trying to connect, as opposed to believing that you're already on net. And there are various other security problems: the evil twin attack, the session hijacking, there's Wi-Fi phishing, and so on. Okay. A second a problem area is really to do with encryption. So as opposed to your private home Wi-Fi setup, in the public one, particularly non-encrypted sites, there are several kind of hacking tools that are actually exposed that actually create a more dangerous environment. And this particularly makes the experience that you have in a public hotspot from a usage perspective a challenging one. Again, not directly tied to your speeds. It, however, does add some overhead here in terms of your experience. Probably a more annoying and definitely adding to the experience of what speeds you see is the number of SSIDs your device is scanning as it transfers, looking across the network. And a lot of these are actually maybe closed networks and may not directly be unwarranted from what you're trying to connect to. However, this is a symptom of a bigger problem we'll talk about related to interference, and particularly in dense urban areas, in buildings where you have perhaps within a certain short geographic area tens of wireless access points visible. this actually is a problem because of the limited available of channels and the specific technology employed by that Wi-Fi access point. If it's on a 2.4 gigahertz, for example, the limited number of channels you have, the amount of interference that you're exposed to, as well as the limited channels, your experience is going to be fairly poor. The other is effectively coverage shrinks as you have more networks available, because the one with the more dominant signal strength will take over. So these are basically annoying connection processes. However, they contribute significantly to the experience and the throughput experience for the subscriber. So kind of a logical connection with the number of SSIDs scanned is interference and the spectrum issues. So let's talk about the 2.4 gigahertz band. This one is the one that's been around for a while. In North America, it's the 3 channels that are really available, and these are shared by a lot of other devices, ranging from other things from I think cordless phones to baby monitors to some Bluetooth devices, and each of these then has a direct correlation into the actual signal-to-noise ratios, and contributes to spectral efficiency and the actual real bits per hertz that you can pack in here. You don't quite have the same level of problem in the 5 gigahertz band, but by the propagation properties of the spectrum available, the range of coverage for a 5 gigahertz radio is a lot less than the 2.4 gigahertz radio. So basically, while you have a relatively less cluttered band, you do have a shorter range. So you to get the same level of coverage, you had to put more radios out there. Also, not all the 24 channels are useful, primarily because of some regulation that went in to open up this band. There's a dynamic frequency selection required, particularly to avoid radar, military radar, and government use of that spectrum. And these DFS mechanics are implemented into the wireless access points. So that actually adds to some of the complexity in channel selection. As a result, some channels are not available based on whether radar is detected, the strength of it, the time it's occupying that channel. And then some channels are actually better for outdoor usage. Actually, Wi-Fi works better outdoors, as you can imagine, based on the propagation qualities than indoor. And with indoor, the various building materials, you actually end up having a lot of variability in coverage. And then another issue, obviously, is that if you have some legacy Wi-Fi devices that are not compatible, the actual utility of having a 5 gigahertz band is diminished. So that's another aspect of interference and spectrum issues that kind of have a bearing directly on the speed and the experience of for the user. Another part of the user experience, and this is more so in kind of public Wi-Fi, is taking the assumption that you have ubiquity in Wi-Fi access and you compare it to your cellular experience. You don't have what we term as a seamless connection where you go between Wi-Fi access points. Even on a campus, going across from where you have ubiquitous Wi-Fi on a campus, as you're making a connection and you're walking, or you have some level of mobility associated with your session, you don't have a seamless handoff, and you typically have to re-authenticate at the server end to determine that the subscriber changed from one cell to another is also not maintained. And from a service level, the navigation associated with that is not available. So that is another difference or differentiator between the Wi-Fi experience and a mobile experience, and this is one of the problems that is being addressed by the industry. And there's a couple of ways of where this is being looked at. From a standards perspective, there's a capability referred to in short form as MDSF, stands for Network Discovery and Selection Function, and this allows your mobile devices that are typically integrated, with Wi-Fi and your mobile service, your cellular service, to basically get authenticated and support roaming across networks. And this level of seamless network access actually drives a network design need to manage placement of wireless access points to provide the best ubiquity, the best handover experience. And that is one of the network design or optimization problems that is actually an industry-wide problem, particularly for public Wi-Fi spots in metropolitan areas. And the target for these are subscription-based services where you're doing some data offloading for cellular service providers, and in general for Wi-Fi service providers that want to integrate Wi-Fi and the mobility experience, particularly as handsets and smartphones have both Wi-Fi and wireless in there. So as we kind of look at kind of the future for Wi-Fi, and we look at the standards coming about, the 802.11ac standard, which is under development, this is actually designed to kind of improve that speed or throughput aspect in the 5 gigahertz band. It is designed with a wider RF bandwidth, 80 to 160 megahertz, more than the 20 megahertz that things are used today. Allows for kind of the higher density modulation scheme, the 256 QAM. That provides increased spectral efficiency that we talked about earlier, and you kind of get a single link throughput that you can actually sustain at greater than 500 meg, and multi-session throughput at greater than gig. And you think about the backhaul technology required for this will typically be gigabit Ethernet or fiber fed into these areas. So again, designed for much higher speeds and applications that actually are, to some extent, are in use today, but trying to extend it for multi users. And the technology kind of to drive it, kind of extending of what you have in 802.11n to 802.11ac, is a 3 antenna based one. Today, 802.11n, which is I think a lot of wireless access points that you buy today are automatically 802.11n, do have multiple radios, and they do support MIMO, multiple input, multiple output capabilities. The beam forming technologies in 802.11ac actually amplify and extend that capability to increase throughput. So kind of to summarize, and I will kind of pose some of the optimization problems. I think public Wi-Fi has many problems that you experience today. I think security as an aspect that we all deal with at a logical level. At a physical level, you certainly see the lack of quality of service where there's no fairness in terms of subscribers in different applications, and greedy applications can grab the bandwidth. Direct correlation to the speed experienced. And then you have configuration challenges there related to what spectrum it's used, what technology is used, and how you manage that in a public Wi-Fi environment. And when you compare the home network connections that are more deterministic, you actually have an improvement in kind of the consumer broadband available, and you also have a set of application management that, as a user, you control in the deterministic admission control that you can support in your own home network. And while there are some new technologies coming in with the Wi-Fi passport for the network authentication and selection and the 5 gigahertz to solve some of the public Wi-Fi problems, there are going to be some network design and commercial challenges that are going to be more traditional optimization ones. So as an example, I think showed you on the kind of one of the first slides the density of Wi-Fi in a metropolitan area like San Francisco. If you had to go design a public Wi-Fi network that tried to take from a two-dimensional perspective the least number of Wi-Fi access points to place in a city like San Francisco to get ubiquitous coverage for subscribers who want to do handoff and go across that. What would be that minimum set be to get maximum coverage? Now, once you solve that, you realize San Francisco, as any dense urban area, has a lot of high-rises, and you've got to think of distance and coverage not just as a function of a two-dimensional problem, but a three-dimensional problem. And that says, how do you place your Wi-Fi access points or turn them up, light them up, as a basis of a 3D problem. So that's an example of an optimization problem you would have from a network design. Now, while we saw the city of San Francisco already has a lot of density of Wi-Fi access points. Now, if you took this as a social network challenge and you looked at a concept like your own social network or your extended social network to say, if they would allow you to auto-authenticate, okay, that everybody 4 friends removed in your Facebook community, just the city of San Francisco would auto-authenticate you, how many access points would you want to turn up, or how many friends would you need to go have in your network to get that ubiquitous San Francisco? Okay? And these are actually very real problems because there are social networks that are embracing Wi-Fi as a way to have a way to both quote rent out your Wi-Fi as well as get you to access your friend's Wi-Fi without having to ask people for the wireless encryption password. If you kind of extend this further to a pricing model to say, how would you price or incent subscribers who or owners of Wi-Fi access points to open up their network to your social network or to a community? And you could base that based on how much Wi-Fi is available, how much interference is there, and the ideal placement. So again, you can extend some of the pricing optimization problems to the Wi-Fi one. And last but not least is kind of the location, the physical location of placing a Wi-Fi access point is an optimization problem in itself because we're trying to minimize interference. Today, all the Wi-Fi access point placement is ad hoc, right? You just kind of place it, and in the unlicensed spectrum, watch for how service is, and then you try to tune it. If you had to go make your placement based on that, that kind of provides another inherent optimization problem. So, and just kind of in summarize, I think this question that Mang posed very relevant to us, both in kind of the private and the public space, and certainly provides a lot of different optimization opportunities. So.